So we humans come with 10 fingers, which make us very adept at counting things in sets of 10. We even have a name for the system. It's called the decimal system, or base 10. So to review, for all you people who have forgotten kindergarten, we would count like this. 1, 2, 3, 4, 5, 6, 7, 8, 9, and one set of 10. And the only digits we use are 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. But what if we hadn't come with 10 fingers? What if we'd come with, say, 8? Then, I'm guessing we would learn to count in sets of 8. We might have had a name for it, something like the octal system, or base 8. We would learn to count like this in kindergarten. 1, 2, 3, 4, 5, 6, 7, and one set of 8. And the only digits we'd need would be 0, 1, 2, 3, 4, 5, 6, and 7. 8 or 9? We wouldn't even know those existed. Okay, forget about 8 fingers. What if we'd only come with 2 fingers? Then I'm guessing we would learn to count in sets of 2. Maybe we would have called it something like the binary system, or base 2. And in kindergarten, we would learn to count like this. 1, one set of 2. So the only digits we would need in this system would be 0 and 1. Wouldn't need anything else. So what if we went the opposite direction? What if we had 16 fingers? Then we would have learned to count in sets of 16. And they called it hexadecimal. Or some people call it hex, which is base 16. We would count in sets of 16, so it would have gone like this. 1, 2, 3, 4, 5, 6, 7, 8, 9. And we know we want to get to one set of 16, so what do we do with these? So we're going to go with A, B, C, D, E, and F. So our digits in base 16 would be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, and F. 16 digits. So back to base 10, where everybody's the most comfortable. So let's take a number like 43. We all know that is 3 in the ones column and 4 sets of 10. We have a number like 543, that's 5 hundreds, 4 tens, and 3 ones. We can keep going this way as far as we want. So this would be the thousands column, this would be the 10,000s column, this would be the 100,000s column. We can keep going that direction forever. So we have ones, tens. This is 10 sets of 10, so 10 times 10. We can also call that 10 squared. This is 10 sets of hundreds, or 10 times 10 times 10, or 10 to the third, 10 to the fourth, 10 to the fifth. We can keep going that way for those also. So this would be 10 to the first, and 10 to the 0 power. So if we had 3,554, we have 3,000s, 500s, 4 tens, and 3 ones. I think we all got that. So this pattern is going to work exactly the same no matter how many fingers we have. So let's try and fill out this grid for our 8-fingered friend, base 8. So starting from the right, we have the same thing. We have the ones column. We have one set of 8s, and then we would have 8 sets of 8. 8 times 8 is 64. That's 8 squared. And we have 8 sets of 64. 8 cubed. 8 to the 4th power. 8 to the 5th power. And on that way as far as you want. So if we took the number 543 in base 8, we'd be talking about 5 sets of 64, 4 sets of 8, and 3 ones. So binary or base 2, same drill. Let's fill out the grid here. So you'd have your ones column, your sets of 2 columns, so 1 set of 2s, then 2 sets of 2s, so 2 times 2 would be 4, 2 sets of 4, 2 times 2 times 2 is 8, 2 to the 4th, 2 to the 5th, same thing, right? So if we had a number in base 2, like 1, 1, 0, 1, 0, that would be 1 set of 16s, 1 set of 8s, no 4s, 1 set of 2s, and no 1s. So hexadecimal, this is going to challenge my ability to write really small numbers. So same thing, ones column, 1 set of 16s, 16 sets of 16s is 256, so that's 16 squared. This is going to be 16 cubed, 16 to the 4th, 16 to the 5th. So 16 times 256 is 4,096, and this will be 65, 536, and writing really small, 1,004,8,576, that's a 7. So if we had a number like 2610, 2 sets of 4,096, 6 sets of 256, 1 set of 16, and no 1s. So let's count this many things in base 10, 2, 8, and 16. So your 10-finger base 10 decimal thinking brain looks at this picture and comes up with 19 really quickly. And you'd be right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 1 set of 10s, and 9 ones. Let's count this many things in base 8. That would look like this. 1, 2, 3, 4, 5, 6, 7, 10, 11, 12, 13, 14, 15, 16, 17, 20, 21, 22, 23. So 23 in base 8. 2 sets of 8 and 3 ones. Alright, let's try hex next. You guys ready? 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F, 10, 11, 12, 13. So 13. 1 set of 16 and 3 ones. Okay, let's count to 19 smiley faces in binary. Remember, the only digits we can work with are 1 and 0. So 1, 10, 11, 100, 101, 110, 111, 1,000, 1,001, 1,010, 1,011, 1,100, 101, 111. This is making my brain hurt. 1, 0, 0, 1, 1. So 1, 0, 0, 1, 1. 1, 16, 1, 2, and 1, 1. Sounds right. So the moral of this story is we 10-fingered humans are very familiar with these 10 digits. But computers were essentially born with only 2 fingers. They can only deal with these 2 digits, 0 and 1. But they can do it really fast and really well. So you've heard that computers deal in bits and bytes. Well, a bit is just an abbreviation for binary digit, a 1 or a 0, and it's the smallest piece of information that a computer can process. If you take 8 bits and put them together, you get 1 byte. And from that, we can digitize any form of data into ones and zeros. Not just numbers, which is what we've been working with, but text or pictures or movies or music. It's really pretty amazing. So let me leave you with one example. So let's go to our trusty Google search bar and type text to binary converter. Let's try this one. ASCII text to binary converter, and we can type in some human text here, like, now I get a whole can't type binary thing. And if you say convert, there you have it, all ones and zeros.